Hello everyone, thank you for coming. I'm Stránský, this is Andreou and Giulio Fidente. We work on the TripleO project, which is a project for installing and managing OpenStack clouds. And we're among the people who implement updates and upgrades there. So that's what we're going to talk about today. So first, I'm going to do just a short deployment structure recap, just to ensure that we all have a common base for talking about the updates and upgrades. Then I'm going to talk about the upgrades and updates in OpenStack in general. And there are some specific differences in OpenStack between major upgrades and minor updates. Pretty defined, so we're going to mention those. Then we're going to talk about how updates are specifically implemented in TripleO and some of the issues that we faced while implementing the update support. And then we're going to show a demo video with a nice, how does it work that tenants have preserved uptime of their virtual machines during the update. So the deployment structure. This is the overcloud. This is the cloud where tenant VMs run. And it's a simplified deployment, and it's a simplified view of that deployment, just to have the basis for talking about updates and upgrades. There are 3 controller nodes to ensure high availability. There's Pacemaker cluster in it to control the services and help with the high availability. On each controller, there are APIs, RESTful APIs, which users use to talk to the cloud and perform management operations on it. And there are databases which are clustered together to store persistent data, and there's AMQP message bus to facilitate communication between the controllers and also between the computes and between controllers and computes. So for the upgrades, this is the more general case, the major version upgrades. When you do a major version upgrade in OpenStack, the database schema of the services can change, and AMQP messaging, which is used for RPC between the nodes, can change as well. That means that you have to upgrade controllers in parallel, because currently the services can only talk to the database schema or work with the database schema that they expect just specifically for their version. So that means that you have a cloud management downtime. You're going to have to take down the controller services for some time to perform the update and DB schema migration. But that doesn't impact the tenant VMs. They still keep running. And you can upgrade computes in series. In fact, you should, to be able, again, to preserve tenant uptime. And you can also do it in batches, depending how much free capacity you have in your cloud. You can do that because the compute nodes, the compute service itself doesn't have any direct database connection, so it can't have any expectations about the DB schema. And for RPC over the AMQP bus, you can do pinning. So each version supports communicating in its own RPC protocol and also in one version older protocol. You can also do service by service upgrade. That doesn't get you rid of the downtime. You're just gonna spread the downtime by different services. We considered moving to a more service-based management rather than the current role-based management in TripleO. So this is what we might do in the future. But for now, we're focusing on the global synchronized upgrade. So if we were to look at the workflow, first we would pin the Nova RPC, ensuring that we can now have controllers of a newer version, while computes can be also of the newer version or of the older version, and they can still talk to each other. So once we have the Nova RPC, the compute service RPC pinned, we're going to shut down the cluster of the services on controllers. Then we can do the package updates, and if there was some reason to reboot, like a kernel update, we can reboot the nodes. And then once the nodes are back up, we're going to start the databases first, perform the DB schema update in the databases. After that, we can start the remaining services on the controllers, at which point the cloud starts again responding to the management operations and performing them correctly. Then we can do package updates on the computes. We can do it in series or all at once. That doesn't really matter that much. Restart the Nova compute services on them. And if some of the computes need a reboot, that's sort of an added complexity there, sort of an interesting case. You need to reboot only empty compute nodes, because otherwise you would, if you reboot a compute node where there's a tenant VM running, that's a problem for the tenant. So what Nova can do, so first you're gonna remove the the batch of the nodes, or at least one node, from Nova scheduler, which ensures that new VMs being asked, like if someone asks to schedule a new VM in the cloud, it's not going to get scheduled on this particular batch of compute nodes. Then we live migrate the VMs from the compute nodes away to some other compute nodes which are not part of the update batch or upgrade batch. Then we can reboot the compute nodes to make the kernel update take effect, and then we can add the nodes back to scheduler, and we sort of do those batches and until we have restarted all the nodes that needed a restart. And once we're done with that, we do an unpin of the Nova RPC, and your cloud is upgraded to the next major version. So minor version updates, they are sort of less intrusive to the cloud, because OpenStack, by convention, guarantees that database schemas will not change, and IMQP messaging either does not change or is backwards compatible, meaning that you can minor update anything, and it's gonna still be able to communicate with the older version, no problem. So the challenge here is in uptime expectations, because that means you're able to do completely rolling upgrade of everything, and that's what the operators expect. And they expect that there's going to be no tenant downtime, even for the controller part. So we do the rolling updates on the controllers, where we rely on Pacemaker, because some of the more complicated services like databases and the message queue, for example, have a specific set of actions that should be performed while leaving or rejoining the cluster of those nodes. So Pacemaker has that implemented in so-called resource agents, which can deal with this for us really nicely. And then we again do the normal package update on the computes. So let's look at the workflow again. We go sequentially over the controllers. We take one out of cluster, stopping all services there. We do the package update, and then reboot the node if needed. And then we let it rejoin the cluster utilizing Pacemaker, as I said, the resource agent. And then again, the compute procedure is essentially the same. We do updates on all computes, can do them either at the same time or in batches, And then we perform the same reboot procedure as we had before, which includes the removing from scheduler, live migrating VMs away, rebooting the now empty compute node and adding it back to scheduler. And that's how a minor update is performed. Now this is like a very high-level theoretical view. In practice, obviously things get a little bit more complex. So I'm gonna give the floor to Marios to talk about the implementation details of updates in TripleO.
Hello. Hi, can you hear me okay? Hey, thanks. Okay, so, hello. Okay, I don't know how many of you were in Steve Hardy's talk earlier. So I'll do a little bit of a recap on the terminology here. So this is, so the undercloud down here and the overcloud up here is this something that people in this room have heard before, apart from the TripleO people, of course? Is this something you're familiar with or not at all? Maybe? Okay, so what happens is in TripleO, we have two clouds, effectively. We have the undercloud, which is what we stand up, the initial cloud, and that's what we use to manage the actual end user cloud, which we call the overcloud. The undercloud down here is effectively a single node cloud, and that's where we run the director node. And this diagram actually shows the setup, as in this is what we do for the updates. This is the setup that we have. We have a overcloud with our controller nodes, which are running in a Pacemaker cluster to manage all the services. We have our compute nodes, which are hosting the tenant VMs. But it also shows the goal, which is what this is what we want to work towards. And the goal is that with your tenant VMs up here, the director, from the director node, an operator can come in, do a simple CLI command, yum update, and that will then go away and take each of the nodes in the overcloud sequentially, one by one. We'll see how that works in a moment in a little bit more detail, and update them. And the expectation is that there is very little downtime for end user VMs. In practice, from our setups, from our dev setup and our testing, it was in the order of about 10 seconds. You would lose like 2 pings, 3 pings while you're pinging the tenant VMs, and this is while the updates are happening, which we think is acceptable. Okay, I think that's it for this slide. Okay, so we start the update. So the idea is that operator goes on the management node. Steve spoke a little bit also earlier about the plugin that we have to the OpenStack CLI. And instead of before, Steve spoke about OpenStack overcloud deploy. Here we're doing OpenStack overcloud update. The overcloud is the name of the cloud that we're updating, and then we pass in the templates and the environment files, which have to be the same for the update as what you had initially deployed. And the two main things that we rely on here are setting a pre-update hook on each node. What that means in practice is that it sets a breakpoint, okay? And the whole point of this is we only want one node to be updated at any given time. I mean, this is especially important. I mean, it's important for all the nodes, but especially for the controllers, where we want to maintain the high availability. We're maintaining essentially a slightly degraded high availability, because if you're starting off with 3 controllers and you take one of them out, I mean, you're left with 2 controllers. There's still HA, but there's no quorum. If one of them fails, for example, then you're kind of in a bad position. So slightly degraded, but still HA, and also the way we control whether a given node is going to be updated at a given time is by setting this update identifier. And effectively, this is just a timestamp, or just a parameter, a variable, which we will set for a given node, so that when it comes to updating that node, if the update identifier is set, and this is via the heat templates that we use to deploy in TripleO, that node will get updated. Otherwise, it just gets skipped. We'll speak a little bit more about what does the actual updating in a moment. But this is just to show that the two kind of features that we rely on here is the heat native feature to do the breakpoint one by one update of the nodes. We control whether a given node is going to get updated or not by setting this update identifier. So I'm just going to talk a little bit now about what happens on the compute node, and then a little bit more about what happens on the controller node. So the compute node is the simplest case. It's the simplest case because there's no pacemaker. The main things that are running there are the Nova compute and the agents. So we have like the OVS agent, we have ceilometer agents. So effectively, we don't have to worry about bringing the pacemaker cluster down on that node or taking the node out of the cluster, for example. We just once we've made sure that we don't have anything running on that. Well, okay. So Jiří spoke a little bit about rebooting the compute nodes. We didn't actually do that in a great detail. That was the one case that we didn't test too much for the rebooting. But okay, so the simple case is we just update all the packages on that node, and then you go on to the next one. So for the compute node, it's much simpler. For the controller, it's more interesting. Okay, so here we first need to bring the cluster down. So we take the controller out of the cluster. We need Pacemaker to be in maintenance mode for the duration of the update. Once all the services are stopped okay on that node, then we run a yum update. Once the yum update is finished, we put the controller back into the cluster and we go on to the next one. This reference here, the second point about matching the pre and post update environments, that's something that Giulio is going to speak a little bit more about because it was an issue that it was one of the bugs that we hit, in fact, because we had a change in the Pacemaker constraints from what we had initially deployed to what we were updating to. So we needed those to match for the update to work correctly. Okay, so this is how we actually deliver the updates is basically just a bash script. It's called yumupdate.sh, and it's delivered as the config property of a heat software deployment. This is software config. As Steve said earlier, within Heat you can have this software config which runs an arbitrary code on your chosen node. It can be Python or whatever you need to run there. And in this case, we're using a bash script. And if you like, afterwards, if we have time at the end, we can even look. I mean, this is all obviously open source. It's all upstream. You can go on GitHub and you can actually see this script. And you can see that all the logic that we've described here. If it's a controller, you do this stuff. You bring the cluster down. Wait till everything is down. Run the update. Set the maintenance mode for Pacemaker. Run the update. Bring the services back up. Make sure everything is the cluster is settled, and then on to the next node. Yum update, the very first thing it does is checks that update identifier. If the update identifier by default is empty, it's just an empty string. If it's not set to a timestamp, which is what we're using currently, I think, then nothing happens on that node. So the update identifier is set on the given node that we want to update at the given time, and then the yum update.sh contains just that logic. Bring the Pacemaker cluster down, run the yum update, and then bring Pacemaker back up on that node. Bring all the services back up on that node with Pacemaker. Okay, so Giulio is now going to tell us about all the things that could possibly go wrong. Well, some of them anyway. I mean, in theory, it sounds very easy, but there were a lot of subtle things that we had to deal with.
Thank you. Can you kind of hear me? Yeah. Sorry, it's a bit. So, I'm Giulio. So what could possibly go wrong? We have a plan, and we have an implementation, and we have bugs. So, like every software that I've seen. And the interesting thing about talking about the bugs is that we learn a lot from the bugs. I get to deal with bugs a lot. So these are not just the 4 bugs that we hit, are just more like 4 different type of bugs that we had to face and that we had to deal with. And so they kind of go into different areas, and they also are, they will show how far we had to reach, especially in taking help from other people to get all the things to work. And so the 4 different types. Let's see. One is what I'm calling the tooling bugs. It's just issues in the tooling that we use to run the update. So not tools that we manage by ourselves, but tools like Heat that Steven actually introduced before us. And another type of issues is bugs in the workflow. So bugs in the way we have implemented the update, which is actually causing troubles that we didn't think about in advance, or at least that we didn't think correctly during the planning part. Then there are what I call subtle bugs, which are problems caused by existing bugs or maybe old bugs in the actual components that we are trying to update. So not in the tooling that we use, not in the workflow, but just components not behaving as they should when they are performing the update. And evil bugs, so those which we introduced by ourselves, the worst ones, right? The ones that we feel responsible about more than the others. The first one, it looks like an easy issue. We have each and every resource of our overcloud. Well, we have a representation of each and every resource of the overcloud in Heat, including the networks. So Steven at some point said that we have network isolation, so we have multiple networks and multiple sub-networks in the undercloud neutron, which are actually matching the physical networks of the overcloud. And Heat had a very nice feature that introduced it during, after our initial release, which allowed us to refer to networks by their names rather than their IDs. And we decided to take advantage of this feature. So in the initial release, we were referring to the networks from their IDs. Then in the next release, we were referring to the same network by its name. And we expected it to do the mapping correctly, and they surely were also. But it wasn't working as expected, so we ended up with the overcloud, deleting and then creating a network which was causing cascading issues. So we had to go through actual Heat experts, Steve in this case, who not only had to fix the bug in the master version, but also to backport it to the stable version, which we were trying to update to, right? So there's twice the work because it's on the master and it's also the backporting phase. We wanted the feature to work in the version that we are updating to. Otherwise, we can't actually take advantage of the feature. The other bug that I had in the list, it's a kind of, very different area, but not really in the tool itself. So we use Pacemaker in the controllers, and Pacemaker is doing its job as we want it to. And it has a sort of graph representation of the services so that it has some understanding of which one depends on each other. And during the update, as they were describing, we need to do some controlled shutdown of the services so that they get down in a cleanly manner and we can take out one node from the cluster without the other behaving unexpectedly. And the problem is we had a problem in our constraints, right? In what represents this graph in Pacemaker. So we were unable to do a clean shutdown of the services. The problem was we knew about the problem. We just updated the constraints in the newer release, but we were running the update, so we needed the shutdown before the update itself. And so we were actually going through the graph before it was updated to the working version, which means we were running through the graph in the broken version. And this is why I call it a workflow problem, because we had to perform a matching of the pre and post update of the constraints before the actual update was started, before the actual YAM update could start. This time, HA people helped. One of the guys is there on the first desk, Mikael, and he helped us figure what was the proper graph to put into Pacemaker to make all the flow work as expected. Another bug, again, which needed help from other people, and this time from Neutron course. I don't know if there is anybody from Neutron in the room or not, but So we finally got Hit to behave as we want to. We got the constraints in place as we need before the update, actually. We run the update. The software is updated as we want it to, but we also need to preserve the guests' connectivity, and we figured that something is wrong, like guests are not working during the update. This is actually a problem in Neutron, and it took us probably a day to figure before we could reach the appropriate people. And it turns out to be a bug which was fixed in Neutron, but not in the version that we were coming from. A very simple bug. It was just the keep alive. We use a feature from Neutron which allows for H availability of the L3 IP, so of the float of the agent which is running as the L3 router. And this is implemented by having multiple copies of keep alive D running on all nodes. So during what we hoped to be a clean shutdown, Neutron was not correctly killing one of his keep alive D instances, so the actual IP was not relocated over the other. This was not a problem with Pacemaker, this was actually a problem with how the thing was implemented in Neutron. So again, we had to put in place a workaround which was distributed on the nodes through Heat before the actual update could take place, because we really needed the IP, to relocate before the update so that the guests wouldn't lose connectivity. And then another area, again, the evil area, the area where we are responsible for. And so update is complete. Heat worked as expected. Pacemaker did the shutdown. Neutron did the relocation. The guests have connectivity. Everything seems fine. And yet there is people testing this after the update, and they are doing basic stuff like scaling the cloud after the update, and it's not scaling anymore. Like, how is it that was working and it's not working anymore? And this is probably, I forgot it in the slides, excuse me, but this is actually the update identifier that Marius was talking about, because Heat tries to be clever about when it's necessary to update the resources and when it's not. We just forgot to distribute the update identifier to the tool which was setting the maintenance mode and stuff. So on the first attempt, on the moment when the resource was created, it was doing what we expected. But at the moment when the resource was updated, it wasn't, because the update identifier was not changing. It took probably more time to get to our working implementation than to do the initial implementation. So, just to give an idea of how much we spent to get it working. But we have a video now, right? Because finally it did work. So let's see the video and how it actually, works.
Thanks. So just one last thing on this slide. One of the reasons we had this here was to call out. As Giulio said, it was evil. It's kind of subtle, because the update was successful. The update was complete. The cloud was working. The tenant VMs were fine. And this was to call out some of the work that people like Marius Cornet up there and the testing guys were doing, because they really tested it. Even after everything was working fine, they put it through its paces. They tried scaling, adding, and removing nodes, and things like this showed up. So sorry about that. So I'm gonna attempt to show the video. Unfortunately, with the updates, it takes so long. It's really not feasible to. Can you hear me okay? Yeah. It's really not feasible to do a live demo. Even with a very small setup of 3 controllers and a compute, take best part of at least an hour, to get the whole update through. Why? So hold on. So okay, the video is not great. I don't know how well it's going to work, but I'm gonna skip through, and because we're also almost at time for the half hour to leave some time for questions. The main thing I want to demonstrate here is the route of failover, really, to show. Well, the main thing I want to demonstrate is how the tenant VMs remain available and they kind of go down, or you lose 2 pings throughout this whole process. Okay, so I've got some times here on my phone which I'm going to skip to. Okay, so initially, let's go to here. Okay, so, oh, actually, hold on, sorry about that. Yeah, okay, let's start right at the start. So, okay, this is the setup, okay? At the top there, we've got the heat stack list. So you see I've got a heat stack deployed. I've got my overcloud deployed. It's create complete. There's 4 nodes involved here. So you see the ironic nodes, and you see the Nova instances at the bottom corresponding to those nodes. So we've got 3 controllers in HA, controlled by the Pacemaker, and we've got the 1 compute in this setup. And then I'm going to skip to here to show you what's happening on controller 0. So this is a terminal into controller 0. The output you're seeing here, again, I mean, you don't really need to see, well, okay, it's pretty bad, but I'll try and point at things. What this is showing is an IF config on the Neutron router namespace, okay? And the main thing I want to show is this line here, which shows that the tenant router IP is currently being hosted by this controller, okay? So it's on controller 0. And we'll see in a moment that when this particular node gets updated, that IP goes from here and gets failed over to one of the other controllers. It's not being updated, okay? And that means that you can still get to your tenant VMs, which are being hosted on your compute node. Okay, so let's go to where the update starts, so you can see what the CLI looks like in practice. So this is what the operator would do on the director node, OpenStack, overcloud update stack, and begins the update. And this will pick one of the machines based on the breakpoints, pick one of the machines and start updating that one. So let's go to a first breakpoint to show you. So yeah, actually that's here. So you can see, hold on, go back slightly. Yes. Okay, so that will come up in a moment. So you see here, that's hit a breakpoint, and it's picked controller 2. I think this is, yeah, so it's picked controller 2 here. It's waiting for some input from the operator. You want to start updating this controller, you say yes, and it starts running the update on controller 2. I'm going to actually skip forward here to where it's updating controller 0, so we can see the router failover. Actually, I'll do that. So go to 7. Okay, so the text is very small here, but what this is showing is that, I mean, I intentionally made the text much smaller here because I didn't want you to see so much what was written, but the fact that this is a growing list of services which are Pacemaker. This is the output of PCS status. So this is the status of your Pacemaker cluster. And it's showing that on controller 0, because it's being updated now, all the services are coming down. So this list grows with services which are coming down on that particular controller, okay? And I will skip to this point where you can see now that this is controller 0, which, remember, this is the one that was hosting our tenant router. At this point now, and this is, hold on. Okay, so this is controller 0, and then we'll see here how the IP will appear on, so you see the cursor in the video is, oh, damn it. Sorry. Okay, here. This is controller 0. You see the router IP is still on there, and then it's gone. It's gone from there, and it just appeared on controller 1. Okay, so it fails over. And what that means is if you see where we're pinging the overcloud tenant instances, hold on, I need to just find this one point, and then I promise I will leave some time for questions. Yeah, so this is what I want to show you here. Throughout this process, we're pinging the tenant VMs, ping, 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 and it's fine. Those 2 unreachables is the time it takes for that router failover to happen. So in practice, it's about in the order of 10 seconds of downtime, well, not being able to reach, not even downtime, not being able to reach your tenant VMs. Yeah, so that's the demo video, and I think we have a few minutes for questions. Thank you. Any questions?
Yeah, I have a question regarding the updates. can also run some tests of the environment that is actually in the position as before.
Yeah, that's a very good question. The question was, do we do any validations on the update? So right now, not. There has been some work. So Steve has done some work on checking the heat resources. Is that right? The pre and post update heat resources matching?
There's some work going into runtime validation. A pluggable architecture that allow you to do those kinds of checks. Right now, they're not built into the system, but they will be.
Yeah. So right now we do have this simple checking of the heat resources, but I mean the actual validations and doing more comprehensive validating of your environment, and that would apply not just to the post-update environment. It would apply. I mean, it's something you would use in general to the cloud that you've deployed. I mean, yeah.
Let's say you have a security vulnerability and you patch it, and you need to verify that it's actually patched.
So I wanted to say one thing. If it's about the configuration, if the question is about the configuration, we use Puppet, which is meant to enforce the state. So if Puppet succeeds, then you can either have the exact configuration you had before, or you may even have updated the configuration, so slightly changed something. And if Puppet is okay, then I mean, that's our first guarantee that something actually happened. If the question is more about the the versions of the packages which you have, because this was actually running on CentOS in the demo, then no. But I think there are probably other tools which fit better the scope of.
Okay, so can you mention any tools for, let's say, deployment validation, the update validation that is actually still valid, and you can say like it's working, even the scaling up, is working. So how would you validate it?
Oh, so like Tempest or I'm not sure what is on your. I'm
thinking about the Tempest too, but yeah.
But like in a lightweight version, or.
Okay, so
it's a good idea though
to use Tempest.
Yeah, it's a good idea to use either Tempest or a subset of the existing tests in Tempest.
The idea is that there's going to be a couple of different levels. I mean, it's going to be the idea. The vision is that we're going to have a pluggable validation implementation that you can write your own validations for. But I mean, just to point out, there's a couple of levels of validations there. I think you're talking about validating that your cloud works, but there's also things like validating the imports, validating a conflict between
I
params.
think the Tempest is more like for the developers, right?
No, or it's for operators.
Or for okay.
Yeah. So one of the So one of the options would be Tempest again, or we have actually a couple of people working on a external validation tool, external to Heat. I'm not aware that it's been integrated into RDO yet. I don't think it has, but there's some work on it. And there's another option. Láďa Smola had a talk before showing CloudForms integration with the director or manager, and he had this checks there built in for the package versions, for example, to verify that you're not vulnerable from shell shock or bugs like this. So the other option would be to integrate with something like ManageIQ.
Okay, that answers.
It's different on many stages.
Maybe we have time for one very quick question.
Is there support for rollbacks?
Rollbacks.
I don't think there is, and I'm not sure how would we implement it really. Like you can of course you can do backups and then roll back manually from some backups. But once you do a YAM update and do a bunch of config changes, do the database migrations, those, as far as I know, those aren't reversible by themselves. So you would really need to do like a complete rollback.
That's
I think.
for upgrades, but I mean even in the updates for the database. Because we're not changing versions for the updates, but even then, no, we don't currently know.
Yeah.
There's a documented process though, which if things went that badly wrong, you would permanently exclude the zone from the cluster until the replacement. So you would avoid rejoining the cluster, drop it out of the cluster and use switch over the replacement. That would be one practice.
Right. Okay. Okay.
Thank you very much. Thanks.
you have a question, yeah, you can come. Thank you.